This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today we're diving into a paper that explores a new framework for integrating causal inference with deep learning. The paper, Causal Deep Learning, proposes a way to leverage partial causal knowledge and quantitatively characterize causal relationships, even in complex, real-world scenarios. What are the key challenges that this paper addresses?
The paper tackles the limitations of traditional causal inference methods, which often rely on strong assumptions about the causal structure of the system. These assumptions are often untestable in practice, making it difficult to apply causal inference to real-world problems. The paper also recognizes that deep learning, while powerful, typically lacks a framework for incorporating causal knowledge.
So, how does this new framework, Causal Deep Learning, CDL, address these challenges?
CDL introduces a three-dimensional framework for thinking about causality. The first dimension is the structural scale, which captures the level of causal knowledge we have about the system. This ranges from having no knowledge about the relationships between variables to having a complete causal graph.
Can you elaborate on the structural scale?
Imagine we're studying the relationship between smoking, cancer, and death. At the lowest level of the structural scale, we have no knowledge about how these variables are related. We simply assume they might be dependent. As we move up the scale, we incorporate more knowledge, such as the assumption that cancer is the reason why smoking is related to death. This can be expressed statistically as smoking being independent of a death given cancer. At the highest level, we assume we know the exact causal structure, such as smoking causing cancer, which in turn causes death.
So, CDL allows us to work with partial causal knowledge, which is more realistic in real-world settings. What about the other dimensions of the framework?
The second dimension is the parametric scale, which captures the type of assumptions we make about the functional relationships between variables. This ranges from making no assumptions about the functional form to assuming a fully known model.
Can you give an example of how the parametric scale works?
Let's consider the relationship between drug dosage and patient recovery rate. At the lowest level of the parametric scale, we make no assumptions about the functional form of this relationship. We could use a non-parametric model, like a neural network, to learn this relationship. At a higher level, we might assume a linear relationship between dosage and recovery rate. This would allow us to use a simpler linear model, but it would also be a more restrictive assumption.
So, CDL allows us to choose the level of parameter assumptions based on our prior knowledge and the complexity of the problem. What about the third dimension?
The third dimension is the temporal scale, which captures the impact of time on the causal system. This is important because causes typically precede effects. CDL allows us to model how causal relationships evolve over time, which is crucial for understanding dynamic systems.
That's interesting. Can you give an example of how time can complicate causal relationships?
Consider the relationship between a person's exposure to a certain environmental factor and their health outcome. The effect of this exposure might not be immediate, but rather manifest over time. CDL can help us model these time-dependent effects, which are often missed by static models.
So, CDL provides a comprehensive framework for incorporating causal knowledge into deep learning models. How does this framework help us construct and test model pipelines?
CDL allows us to identify the right type of transition in knowledge, which is the difference between the a priori knowledge we have about the system and the a posteriori knowledge that the model learns from the data. We can then construct model pipelines that bridge this knowledge gap.
Can you give an example of how this works in practice?
Imagine we want to generate fair synthetic data using a generative adversarial network, GAN. This GAN requires a known causal graph as input. However, in many real-world scenarios, we don't have access to a fully known causal graph. CDL allows us to construct a pipeline that first learns a causal graph from the data and then uses this graph as input to the GAN.
So CDL helps us to build more robust and reliable models by carefully considering the assumptions we make and the transitions in knowledge that occur during the modeling process. What are some of the key contributions of this paper?
The paper introduces a new framework for causal deep learning that allows us to leverage partial causal knowledge and quantitatively characterize causal relationships. It also provides a clear way to categorize and compare different CDL methods based on their structural, parametric, and temporal assumptions.
This framework seems to have the potential to significantly advance the field of causal inference. What are some of the limitations of CDL and what are some potential future directions for research?
One limitation of CDL is that it still relies on assumptions, even if they are more flexible than traditional causal inference methods. Future research could focus on developing methods that can learn causal structures and relationships with even fewer assumptions. Another area for future research is to explore the use of CDL in more complex, real world applications, such as personalized medicine, climate modeling, and social science research.
So, CDL is a promising framework for integrating causal inference with deep learning, but it's still an evolving field with many open questions. What are some of the key takeaways from this paper?
The paper highlights the importance of carefully considering the assumptions we make when applying causal inference to real world problems. It also emphasizes the need for a more comprehensive framework for integrating causal knowledge into deep learning models. CDL provides a valuable starting point for this integration, and it has the potential to unlock new insights and applications in a wide range of fields.
Thank you for this insightful discussion on causal deep learning. It's clear that this framework has the potential to revolutionize how we approach causal inference in the age of big data.